Hi. So today is the last part of this section, and we are going to analyze your results. So hopefully, in the last lesson, basically, the last thing you should have done is calculate the specific heat capacity of the two materials. One was water, and the experiment that I did, and the other one was aluminium, which was just pictures. And this is the sort of thing you'd need scientific equipment to do in a science lab, which we are not in, so we can't do that. So we'll have some data, and then we can compare, and then we can see whether we were brilliant or not very good, and then see why, and just answer some questions. I did this for you the other day, the starter. It's just examples of how to raise the energy or temperature of something, but it's a good place to start. Let's review. So using the equation, energy is mass times specific heat capacity times temperature change. Calculate how much energy is needed to raise the temperature of water by 5 degrees. Then calculate how much energy is needed to raise the temperature of water by 5 degrees, but twice the amount, and 1 kilo by 10 degrees. I forgot to give you the specific heat capacity of water is 4,200. Okay, pause the video and answer the questions, and then unpause and see whether you've got it right. Do it. Okay, so I think you've had enough time. So let's check. The first one just says calculate how much energy is needed to raise 1 kilo, of water, 4,200, times temperature change, which is 5, which if we put those together, is 21,000. The next one is how much energy is required to raise the temperature of 2 kilos. So 2 kilos of water times 5. Same thing, but twice the amount. So it's just going to be double that one. 42,000. Indeed. And the last one, how much energy is needed to raise the temperature of 1 kilo of water? So 1 times 4,200 times 10 equals the same, 42,000. Okay. So, yesterday when you watched the video of me doing this, so what I did was I put some water into a kettle. I put 488 grams, which if you convert is 0.488 kilograms. The water started at 24 degrees and it boiled, so it finished at 100 degrees. I even took the temperature and it was 100 degrees. So that means there is a temperature change of 76 degrees. The joule meter or the power meter that was plugged into the kettle showed on average 3,000. Sometimes it was a bit higher, sometimes it was a bit lower. And it ran for 74 seconds. So what I did was I took these 74 seconds here, and then I multiplied it by the power here. And that gave me this answer, which is 222,000 joules. That is how much energy the kettle gave up during that period of time. 222,000 joules. So let's stick those things into the equation. We know energy, we know mass, and we know temperature change. So we can use those to work out specific heat capacity. And so that's, here it is. I'll do it again just so you can see. Energy all over. Mass times temperature change. And if we stick those numbers in, 222,000, all divided by 0.488 times 76 gives us 5,985 joules, kilogram, Kelvin, or degrees. It's quite rubbish. It's quite far off. It should be 4,200. Well, and we got nearly 6,000, so 1,800 too high. That's not good. Let's have a look at the other experimental data that was given to you. We have a massive block of 1 kilo. Smart, 1 kilo. Starting temperature, 22 degrees. Highest temperature, 36 degrees, which gives us a potential, temperature change of 14. The potential difference was 11.8. The current was 2.3 amps. It ran for 115 seconds. So first of all, the equation we need is power is equal to current times voltage. And that power ends up being 11.8 times 2.3, which is 27.14 watts. Okay, so that's just power. Power times time is energy, which I've done here. Power times time is energy, which gives us total energy of 13,868. So now we have energy, we have mass, because it tells us the mass here. We have the temperature change, because it was 36 minus 22, which is 14. And if you put those numbers in, it can get the specific heat capacity, 13,868, divided by 1 times 14, gives us 990. The real value is 900. That is much better. These people, they faked it. They lied. It's never that good. It's never that good. But hopefully those are the values you've got, because you have the same numbers. If you didn't, maybe just correct it now. You need those numbers. Okay, so first of all, let's look at some of the things that could have happened. While the experiment is running, energy is transferred to the surroundings by heating, because the insulation does not stop all of the heat transfer. Basically, the kettle, if you touch the outside of the kettle, it was incredibly hot. It was very, very hot. It's metal as well, so it's a conductor. The aluminium block one was wrapped in insulation, but yeah, loads of heat was wasted. If there was no heat waste, if there was no heat transfer to the surroundings, would the measured temperature change have been larger or smaller? So if we had the thing running for the same amount of time, would the temperature change have been larger or smaller? There was no insulation. Sorry, there was no loss. The insulation was perfect. If there was no heat transfer to the surroundings, would this have made the calculated specific heat capacity higher or lower? So the first one is, if we didn't lose any heat to the surrounding, would the temperature have gone up more? And then the second one is, if there had been no heat to the surrounding, would it have made our calculation of specific heat capacity higher or lower? I hope it wasn't higher for their water one, because it was already pretty rubbish. And then, describe one way, apart from using insulation, you could reduce or remove error from our experiment. How could we do the experiment better? What things could we do? The kettle one, for example, I turned it on, and then I turned it off, and then I let it turn itself off, whereas it could have been boiling already. So maybe what I should have done was be constantly taking the temperature and then stop the timer or turn it off when it was reached 100 degrees, not rather than when the kettle clicked off. So maybe that was a mistake I made. I should have monitored the temperature rather than just allow it to stop off. You can have that one for free. So answer those questions and unpause when you're done. Okay, splendid. Oh, that's not supposed to be the end. What's happened? Something went wrong. There. So, what could be? So, basically, our results aren't brilliant. Okay, one of them is very, very high. The other one is quite high. One's about 1,800 high. The other one's about 92 high, 100 high. So, what could be wrong? I mentioned something before with the kettle. What could be a source of error in our results? And then we've got two results. Are they accurate? And could you describe them as precise? Go back to the previous lesson. We talked about precision and accuracy. Are either our results accurate? Is one more accurate than the other? If one's more accurate than the other, which one? And why would you say that? So just talk about water or aluminium is more accurate than the other one. And then say why. And are they precise? What could you do, maybe, to improve the precision? I've just asked you this, so here we go. How could it be made more accurate? Did we have the best equipment? If you change the equipment, what equipment could you do? What could you do to be more precise? Another method. So all it is just thinking, is this experiment good enough? Your suggestions might be a bit They might end up giving you something similar, but we won't know until we do it, which we're not going to do. But the suggestion is important. I'd just like to see, can you think about the experiment? Remember, so 1, we had a kettle, we turned it on, it boiled the water, it stopped boiling, we recorded how much energy it used from the power meter. The other one was there was a block of aluminium and there's a heater in it, and you put the current through and a voltage, and we recorded the current and voltage, so that tells us how much power went in, and then we recorded the temperature change. So just do one. Is there one that you could have done better? Aha! And now it's just a time for you to practice some questions. So here we have 3 different sets of results for the original experiment, the aluminium one. Now this time, can you put the numbers in and work out what's the energy transferred if we have this much mass, this much potential difference, that much current for that time? Remember, the specific heat capacity of aluminium is 900. So it's just asking you to practice the thing a few times. Practice the equation a few times and get results. And you fill those results in here. Ooh. Also, you could decide, are those results accurate, or are those results precise? And then the last one is just some questions. A bath contains 85 kilograms of water. The water heater raises the temperature of the water from 8 to 38 degrees. Calculate how much energy is needed to heat the bath water. Give your answers in kilojoules. Remember, this is water. Water has a specific heat capacity of 4,200. A 5-minute shower uses 35 kilograms of water. If the shower also heats water from 8 to 38 degrees, calculate the energy saved having a shower rather than a bath. 12. Explain why hot water in a hot water bottle is a better choice for keeping your feet warm at night than a hot aluminium block wrapped in a suitable cover. That would just be weird, but why do you use hot water bottles rather than hot metal things? There is a very logical reason, not just because one's weird. There's very much a definite reason why you would choose water over aluminium. And that's it. Finished. You've done the experiment. I'm sure you did really well. Hope you didn't burn yourself. And hope people worked out the answers. If you have any questions, just ask. But I'm sure you can do all of these things. Okay, love you.